Alrighty, welcome back everyone, and let's get started. So today we are going to start talking about the op-amps, okay? Basic operational amplifier circuits. And the key here is these op-amp circuits are active elements. So it needs power. All right. Previously, like the RC circuit, it's all passive element. In other words, you don't need to, like for example, resistor. Does a resistor need a power? No, resistor is just a resistor, right? But in order to use an op-amp, you need to provide some power, okay? Otherwise, it's going to be like a dead element. And the goal of this lab is that we would like to understand the ideal and the practical issues when you're using the op-amp. And there's going to be something called, I call it as a three-step derivation. And if you understand, it's a very simple thing. And if you understand this thing, then you'll be able to analyze most of the op-amp based circuits, okay? So like I said, I understand you guys have like allergy to circuits and also allergy to MATLAB. However, especially for the circuits, if you just understand this three-step thing, most of the op-amp circuits you can very easily analyze, okay? So that's that. And there are tons of different variations of op-amp circuits, and here we would like to focus on a couple of them, important ones: the inverting, non-inverting amplifier, and the voltage follower, and the comparator circuit, all right? So let's first talk about the ideal op-amp, the ideal amplifier, not the op-amp, okay? So in an ideal case, say you got a sensor, so, or let's call it as a source. For example, it's a sensor. Say you want to measure something from your sensor, and sensor generally generates voltage. But that value is tiny. It's hard to measure. So in that case, what do you want to do? You want to amplify that guy. And when you measure it on the opposite side, you probably would want to have it amplified so that you can really measure it. So the other side here, we call it the load. And for example, it's the measurement system. All right. And ideally speaking, what we want is we would like to have our measurement that is proportional to your original value. Say your sensor reading is very small, you just want to amplify by a certain number, and then you just measure that value. It's a really simple concept, right? Your value you're measuring is like 1 millivolt. Then you want to boost it up by 100 times so that you measure 100 millivolt, which is a reasonable value, right? But realizing this very simple concept in the circuits, it was a real difficult thing. Mathematically, it's just multiplying a simple number, but people came up with a model to realize that thing, and we can make it like a black box. So inside that black box, we have elements like this. And this is plus and minus Vn, and that resistor value is Ri, and this is A times Vn, and this is R out. So you may just think, oh, I'll just somehow have it connected from here directly to there so that we measure something, right? But let's just assume you really actually have it connected like this. Your source through a resistor and another resistor, and it comes back. Then the value you measure here is what? It's divided into two pieces. This voltage is, right? So if you really connect it like this, then your measurement is going to be always smaller because it's divided into two resistors, right? So that's the reason why it's not being connected like that. So it has a closed circuit here, and it has another closed circuit there. And somehow from here to there, the voltage across this resistor is being amplified by a transistor actually, and it becomes A times Vn. And this becomes a new source to run this circuit, all right? We don't know what this is inside. We actually don't care. All I just want is I want this guy to be boosted up and then I can measure it over there, all right? So based on these two circuits, if we write down what Vn is and what V load is, so we focus on this guy first. Vn is what? It's nothing but, it's just a voltage divider, right? This voltage is divided into this resistor and that resistor, and we are focusing on this guy, on that value. And VL is, it's the same thing. Again, this voltage is divided into here and there, and we are focusing on this guy, right? So that guy is times A Vn. If I just sub this thing into here, then VL can be rewritten as A times Ri Rs plus Ri times RL Ro plus RL. So this is what we would like to have actually. And they kind of come up with some idea, and that was realized by doing this thing, all right? But take a look here. This is not ideal. It's your relationship between load and your source is not just depending on some gain A, but depending on the R values, this can change, right? So we would like to remove the influence of this guy, right? So we want VL that is being amplified regardless of the RS from the source, this one, and RL of the load or your measurement system. By the way, these RS and RL is something you can design, but RS is just coming from your circuit, your sensor. Say it's like parasitic resistance or something like that. Maybe this is too large or maybe this is too small. This is not something you can control. And generally, this one too, you can buy a good one that has a certain value, but this is just given. You have an oscilloscope that's just a fixed value, right? So people wanted to make this thing go away. In other words, make this value as 1. So we want to make this as 1. And how do we make this thing 1? These Ri and Ro are something we can control. Again, this is given, right? This is just determined by your sensor, right? So Rs is given, RL is also given. But Ri and Ro, these are something that we can control, right? So we would like to control those values so that this becomes 1. And if we focus on this part, if Ri goes to infinite, what's happening? This guy becomes infinite, this guy becomes infinite. Then infinite divided by infinite, so it becomes 1, right? And what if we had our Ro that goes to 0? Then that means this guy becomes 0. Then this whole thing is RL divided by RL, so it's 1. So this whole thing becomes 1, right? In other words, it's something called the input impedance that goes to infinite and output impedance that goes to 0. All right? In other words, Ri is called input impedance. Rout is called output impedance. This guy and this guy. So again, the story here is we would like to have this thing happen, but that's, like I said, it's kind of difficult. But people came up with this idea, And we can derive this kind of relationship. But in order to remove these influences, you on purpose design Ri to be a high value, Ro to be a small value. So if you make like this, then they go away and you can realize something similar to an ideal case, right? And this kind of theoretical approach is realized by this op-amp, okay? And so this op-amp is the chip that makes this whole thing happen. And this is the symbol of that op-amp. It has two inputs in general, and V plus and V minus. In other words, the input that goes into this plus sign is non-inverting input because plus is not changing the sign. And input that goes into the negative input is the inverting input, okay? We just call it like that because if you have the negative sign, it's like flipping over, inverting, right? And this is your output. And these two prongs are for the supply voltage. Like I said, operation amplifiers are active elements, so you need to provide the power so that it turns on. Okay, so this is just to turn on the op-amp, and these are the input and output. Okay, so you provide input here and output comes out, and this is just to turn it on. It's like, say, for a TV, you just turn on the TV and you receive the signal and then that signal comes out to the screen, right? So these are the real signal part, and this is just providing the power to turn it on. Got that? But if you don't turn this on, your TV is not going to work, right? So you need to have this thing. And if we just use a cartoon to kind of visualize how inside looks like in this op-amp is kind of similar to what we had here. So it has a resistor, and then it has another resistor going out, and then this is kind of transduced amplified voltage, and there are two voltage nodes coming in, just like the closed circuit here. See, there are two prongs like that, right? These are those two prongs, all right? So this is something we would like to focus. And here we had an amplitude gain A, and in the op-amp, we called it AOL, open loop gain, all right? OL stands for open loop, okay? And yeah, V positive, V negative, the difference is going in, and we call the current that flows along these input nodes, we call it IN, and this is output volts. So yeah. And generally, there are two ways to use this op-amp. One is the open loop configuration, and the other one is the closed loop configuration. Okay, so just bear with me. Let's just talk about this open loop, and once we start talking about the closed loop, it will be more kind of obvious. Okay, so open loop configuration is mentioned that we don't have any feedback, so no feedback. Okay, and when the op-amp follows this kind of rule, V positive minus V negative, and that is being amplified into your output voltage. All right, so your output voltage is nothing but the difference between these two being multiplied to this guy. Okay, that is coming out as your output. In other words, it amplifies the difference between voltages at two input nodes. And since we use this kind of condition to realize the ideal amplifier, right? So if we focus on the ideal op-amp assumption here, then those are going to be these. So the input impedance if I write down IMPD, that stands for impedance. Impedance, which is Ri, right? Input impedance Ri, that's going to be infinite. In other words, more importantly, the input current is going to be 0. This is what you're going to use a lot. So let's take a look here. Focus on this part. This resistor is the input impedance, right? And that is infinite. What's the meaning of infinite resistance? Your circuit is broken, it's disconnected, right? Not connected at all. So there can't be any current flowing in and out because you take a look, there's not connected, right? So this guy is 0. Okay, that's the ideal op-amp assumption. Of course, because it's ideal, we call it 0. In other words, in practice, you're going to have a tiny current flowing in or out, but we just assume that as 0. All right, and we have output impedance that goes to 0, and we also have a open loop that is infinite. That's what we assume. But typically, it's in the order of 10 to the 5 to 10 to the 7. So still very large number. And I would highlight these two. So the ideal op-amp assumption is just following this guy, okay, that I explained previously. So it's this and that. But from there, the input current becomes 0 because this is disconnected, right? And then a open loop gain, that is just assumed to be infinite. That's the op-amp characteristics. All right? However, in reality, op-amps are not used as an open loop configuration. And the reason why is, so if I just write this thing again, because even a very small number, a small difference between V positive and V negative, that becomes significantly amplified because this value was what? It was infinite. We assumed this to be infinite in the previous page, right? So say you have 5 volt, 2 volts, so it's 3 volt difference. It's multiplied by infinite, so it's going to be infinite. It's 0.01 millivolt and 0.02 millivolts, so it's the difference is 0.01 millivolt. That one multiply infinite, so again it's infinite. So it's kind of like useless. Everything becomes infinite, right? And being infinite means it's super sensitive. It's like if you don't make it exactly 0, it's going to blow up all the time. So it's all very sensitive. It's really hard to keep it calm, or it's unstable. And the more important reason is a open loop value is fixed, while if you want to change the gain for various applications. So this open loop gain value, it's a very large value, and it's just a determined value. But sometimes you want to amplify 10 times, you want to amplify only 2 times, or you want to change that gain depending on your application. So this is the main reason why people do not use this in open loop configuration.